Good morning and welcome to our note session to talk about Newton's three laws of motion. I want you to watch this video and take some notes because after watching this video, you're going to create 3 slides in your physical science portfolio, one for each law. On these slides, you're going to create your own notes that help you understand each of those laws better. Are you ready? Here we go. So the first law we talked a little bit about yesterday, we've read a little bit about it, and it just says that an object in motion stays in motion, and an object at rest stays at rest unless acted on by an outside force. And we talked about this as being the law of inertia, because inertia is just the tendency for an object to continue to do whatever it's doing. If an object is in motion, it wants to stay in motion, and if an object is at rest, it wants to stay at rest. So in order to get it to do something else, you have to overcome the inertia that the object has. Like for instance, in this little picture here, we have 2 people on a bus that are standing, and the bus hits a stoplight, and you see that both people fall forward. Now, why is that? It's because of inertia. Their bodies were at rest, but in a moving vehicle. So when that vehicle stopped, their bodies wanted to keep moving, and so they bounce into each other. What do you think will happen when the bus starts again? And could you explain that in terms of Newton's first law? If you said that their bodies would be thrown backwards because of the start of motion, you are correct. Now, Newton's second law is all about motion. So anytime an unbalanced force is applied to an object, the object is going to accelerate. That means it has to be a strong enough force to overcome the object's inertia, okay, in order to create motion and acceleration. Now, this amount of acceleration is going to depend on the mass of the object, right? And the amount of force applied. If you apply a small force to a large mass, you're going to get very little acceleration. If you apply a really large force to a small mass, you're going to get a really large acceleration. And Newton's second law is best represented using this mathematical equation where F is equal to ma, or F is equal to mass times acceleration. The F is the amount of force and is measured in newtons. That is the unit for force. Mass we measure in kilograms, and acceleration is meters per second squared. Okay, so it is a change in speed here over a period of time. All right, and we can represent this equation using what we lovingly call the FAM circle. So it is just a graphic representation on how to manipulate or change around the variables to solve for any of the 3 that could be missing. When filled in correctly, we have this, what I like to call a circle T, and it helps to show you what type of mathematical function is going to be taking place. Okay, so we have force on the top here because force is measured in newtons. And we have both mass in kilograms and acceleration in meters per second squared on the bottom. So what this circle represents is that the force on the top could be calculated by multiplying the 2 variables on the bottom. So I would multiply acceleration times mass if I wanted to calculate force. Okay. If for some reason I needed to calculate how much acceleration an object had, I would take the force on the top here and I would divide it by, this is like a fraction bar, divide it by the mass of the object, and that's going to help me calculate acceleration. Likewise, if I need to solve for mass here, I would take the force I was given and I would divide it by the acceleration. And that would tell me how much mass the object had that was moving. So let's do a few examples here. I have a truck at the truck poles, and this truck has a mass of 3,000 kilograms and applies a 7,000 Newton force. And I want to calculate the acceleration of the truck. So the first thing I do is I draw out my circle T, and you don't have to do it this way, but you do have to show work. And this is an easy way to remember what type of math, what kind of calculation you have to do. So I would take what I know. I know I have a 7,000 Newton force, so that goes on the top of my circle. And I know that the truck had a mass of 3,000 kilograms, so that goes on the bottom portion of the circle. In order to calculate the acceleration here, I am simply going to take my 7,000 newtons, and I'm going to divide it by, that's what this line represents here, divide it by 3,000 kilograms. And that's how I'm going to calculate my acceleration. So when I do that, I end up with 2.33 meters per second squared. Now you might be curious is how does a Newton divided by a kilogram make meters per second squared? Okay. And that is because newtons is what we call a derived unit. So it doesn't show you that it has some of the meter per second squared in it. We just need to remember that it is a meter per second squared for acceleration. Okay. So let's do another example. Here I have a soccer ball which has a mass of approximately 1 kilogram, and it is being kicked with an acceleration of 20.5 meters per second squared. So how much force was applied to that soccer ball? And again, if you use this FAM circle, this circle T method, we plug in the information that we know, and we know that the acceleration was 20.5 meters per second squared. And we know that the mass of the soccer ball was 1 kilogram. So when these two variables are next to each other, we're going to multiply them here. So when they're both on the bottom, it is a simple multiplication of those two numbers. So I would take my 20.5 meters per second squared and I would multiply it times 1 kilogram and end up with a force of 20.5 newtons. Now, Newton's third law is usually the most recognizable and easy to remember because for every action force, there is going to be an equal and opposite reaction force. This is something that over the years, students always seem to remember, right? Equal but opposite forces here. Like for instance, with some space travel, once our lovely rocket is rocketing around the universe, you have an equal but opposite amount of force. So as the exhaust comes out of the back and propels the spaceship forward, is propelling it with an equal amount of force. So opposite direction, equal force. Another really great example that students typically remember is tug of war. If you've ever played tug of war, there is no motion over the line when one team pulls with an equal but opposite amount of force. It's only able to be won when one side can pull with more force. Okay, so equal but opposite forces. When you have a standstill in a tug of war, is a great example of that. Okay, I gave an example the other day of leaning against a wall. you have an equal amount of force being pushed up against the wall as the wall is pushing back against you. And so that's your third law in everyday actions. So net force helps us to look at all of the forces that are acting on an object and to determine whether or not that object is going to have motion and in a particular direction. So we can use what we call force diagrams to help us figure out or look at what is happening with an object. And so we're going to keep it relatively simple this year and just look at opposing forces, right? So forces and their resistant forces in opposite directions. So either looking at forward motion and friction, or looking at gravity and the forces opposing gravity. We're not going to be doing any vector quantities, which would be looking at what happens when you change the direction of force and the angles. So that's when you get more up into physics, your senior year, where you're going to use calculus in order to calculate all of those forces. So we're just taking this at a really nice and simple level and looking at opposite forces in the horizontal or vertical direction. Okay, so here I just have a box, and if I apply 50 newtons of force to the right and have an opposing force, maybe somebody else is over here pushing the box to the left with 200 newtons of force. Because those two numbers are not equal, we know there's going to be motion. Okay, so we want to be able to calculate how much force is left over and think about which direction the object would be moving. So in this case, if I took the 200 newtons of force and I subtracted away the 50 newtons of force opposing it, I would have 150 newtons of force left over, and it's going to be moving in the left-hand direction. So in a force diagram, to represent what is happening with motion, we want to be able to see how much force is left over and the direction in which motion will occur. So another example here would be a helicopter. So the helicopter is going to be moving up with 15,000 newtons of force, and of course opposing that would be gravity pulling down on the helicopter with 10,000 newtons of force. So in this particular case, we need to figure out how much force is left over and in which direction would this helicopter be moving. Seems a little obvious that they want to be going up. So here we have the math to show us how much is left over. So 15,000 newtons minus 10,000 newtons is going to leave us 5,000 newtons of force. And we're going to be moving in the upward direction. So force diagrams are another great way for us to represent what is happening in terms of motion. Now remember that in order to have motion, you have to have unbalanced or not equal forces. So you can use force diagrams to represent no motion, but you would have those equal forces there. I hope this was not too painful to get through and that you learned a little bit about the three laws and focused on how to show or calculate force, mass, or acceleration, and how to use force diagrams to represent motion. I would like for you to take the notes that you've taken from this video, go to your physical science portfolio, and create 3 slides. One slide should be for the first law, one slide should be Newton's second law, one slide for Newton's third law, and I want you to place some notes in there that help you understand what each law is, perhaps giving examples of how they're used in everyday life. For the second law, you might want to show some calculations on how you can figure out the force, mass, and acceleration, and whatever else it is that you need in there to move forward. Thank you. I'll see you in a little bit.